Thank you, Lars. It's a great pleasure and honor to be here. It's kind of strange that I'm here to talk about particle physics. I'm a condensed matter physicist, actually a nanoscientist. And so what am I doing here? But it turns out that our field of condensed matter physics has hit on a very interesting particle, the Majorana Fermion. And the search is not going on in an accelerator. You see the accelerator from Geneva. But the search is going on in a chip. So we've shrunk the accelerator down to the sizes of a chip. And what we do is do electrical measurements on a small electronic chip and look for particles. Now, the story of the Majorana Fermion starts actually with Dirac. So there is a, let me do something here that you cannot see. Okay. So the story starts with Paul Dirac, who was actually the inventor of particle physics. So Paul Dirac in 1930 solved his equations and found solutions to his equations. And what he saw was that all the solutions come in pairs. If he has one solution that, for instance, explains the existence of one type of particle, there is another solution that actually hints on the existence of another particle with exactly the opposite properties as the original particle. And what was so amazing about it is that he actually trusted his mathematical solutions. He thought that his solutions, because his equations were so beautiful, the solutions must actually exist in nature. So it was a very bold prediction that the solutions that did not yet describe a particle were a prediction for, as of that time, unknown particles. And he proposed the existence of the positron in 1930, and it was found by Carl Anderson in 1932, very quickly. And indeed, the particle and antiparticle, they have mirror-imaged properties. And so the positron has opposite energy, opposite charge, spin. Everything is mirror-imaged compared to the particle, compared to the electron. Except for the mass. And the mass is still the same as the mass of the electron. Now there are many particles. So how do we know if two particles are actually forming a pair of particle-antiparticle? Well, what you do is you bring them together, and when they come together, they actually annihilate. If they are particle-antiparticle pair, they annihilate, and the mass transfers into energy, a flash of light. Now, Paul Dirac, by believing in his own equations so strongly, actually started the field of particle physics. And it's a very interesting story about the man Paul Dirac. And it's a picture of the book, his biography that came out, I think last year or 2 years ago, entitled The Strangest Man. Yeah, so Paul Dirac was actually a very strange man. And he actually gets the title The Strangest Man. And I think he was called strange. Nowadays, I think we would diagnose him as being autistic. And actually, we would give pills to sort of get rid of it. But in his time, that did not happen. So Paul Dirac could actually live and think in his own world, and not adopt the common view of the physicists at that time, and construct out of his own world his thinking about equations and the existence of particles. And let me stress that this strangest man is really one of the biggest heroes of physics in the 20th century. Now, who can understand a strange man? Well, of course, another strange man. And probably, the strongest competitor for the title "The Strangest Man" was Ettore Majorana, living in Italy in the 1930s, thinking about quantum physics, and playing a little bit with the Dirac equations as soon as they came out. And by just playing a little bit and looking for additional solutions that Paul Dirac missed, he found this one. He found that there's also a solution where the particle is actually equal to the antiparticle. So instead of having it mirror imaged, there is also a solution where they are the same, equal to each other. In the jargon of quantum mechanics, what it says is very simple. This is the formula that defines the particle, is that the operator to create a particle is equal to annihilate or destroy the particle. It's a very simple definition of a Majorana fermion. How can you picture a particle that is equal to its own antiparticle? Obviously, an electron is not the same as a positron, and we don't know any existing fermion that has this property. Well, the way I picture it is by thinking of a half-filled glass. It's a half-filled glass or half-empty glass. And obviously, the half-filled glass is the same as the half-empty glass. It's very obvious. And I would associate the particle with the filled part, and the antiparticle with the whole or the empty part of the other glass. Now, in this case, the particle-antiparticle is just a point of view. Do you live on the positive side of light or the negative side? But as I will show you during the talk, it will actually explain our experiments very well. If you keep the picture in mind of a half-filled, half-empty glass, I think you will understand all our experiments. But let's leave it for now, and let's see what this definition of Majorana actually immediately implies. If you are equal to your mirror image property, then most of your the values of your properties must be zero. That it's the only thing that can be the same if you mirror image it. So immediately it follows that the electric charge is zero, the energy is zero. Actually, also the spin equals zero. Everything is zero except for the mass. And so it's really a particle with not much to say about. It's a nothing particle. And curiously, nothing in Dutch translates to niks. And so instead of having a Higgs particle, we are actually looking for a niks particle. Is there anybody understanding Dutch here? Can that person confirm the translation? It is. It's a translation, the niks particle. So how do we measure a niks particle? What detector can you use that gives you a measurement of something that is zero? And that is exactly the problem, and that is the problem that kept people from measuring the Majorana fermion. It's exactly the reason why it has not yet been detected. So the particle is not detected, and actually there's a kind of a sad analogy with the man, Ettore Majorana. As I said, he was a strange man. And he did his prediction for this particle in 1937. Actually, it gave him the job of professor in Naples, so he was rewarded immediately. But he wasn't very happy. He maybe for psychological reasons, or maybe because of the not so nice pre-war times in fascist Italy. It's not the best time to live somewhere. So he got he had enough of everything. And at a certain day in March 1938, he took the boat from Naples to Palermo. He did buy a ticket, but it was the last thing that people saw of him. He went on the boat, and he disappeared. So we have the very strange situation. Actually, also after his disappearance, in Italy, he's I think people are still looking for him. No, I think it's true. And this piece of newspaper article says, I think it says, I don't know, chi l'ha visto, so who has seen him? And the search for the man, as well as for the particle, has gone on for decades. And what I would like to do tonight is actually report to you the signatures of the Majorana particle. But we also found some signatures of the man Majorana. And so we can also show you, some signature of Ettore Majorana. But we should, start with the particle first. And I said this search for the Majorana fermion has gone on for decades, but mostly in the context of particle physics. And the Majorana fermion has been, could be, a cosmic particle that if you make a detector that is big enough, that, big detector that once in a while you may actually get a measurement of the Majorana fermion. So worldwide there are a handful of these labs, as you see here, mostly underground labs with huge detectors. Actually, if you look into this cave, there's a train coming to bring some equipment. And it's a big size. But the question that these people are addressing is also a big question. Because the Majorana Fermion could be the explanation for the dark matter in the universe. So it's big lab, but it addresses a big question. Now our approach is actually completely different. It starts from a completely different take. And in fact, what we do is we make small electronic chips. We combine different materials in such a way that the particle that lives inside this combined set of materials obeys the same properties of the Majorana. Particle equal to antiparticle. So our approach is entirely different. The size scale is also completely different. Here you see the scale bar of 1 millimeter. And you can take this thing. I do that quite often. I take the thing in my pocket home at nights. So I don't leave it behind. But this is the sample that we fabricated and which we used for the measurements. So these measurements gave some first results Christmas last year. So this is less than a year ago. The first measurements, sort of the indications, were from last year. And I gave a first talk at the American Physical Society meeting in Boston in March this year. And during that talk, people were already blogging and twittering the news. And that started a sort of an avalanche of news reports. And I'm flashing you one here that refers to this experiment as the mysterious particle found after decades of searching. And I guess mysterious must refer to the man Majorana, who was mysterious. I don't know why else this particle would be mysterious. There was another news item from Physics News that says that Majorana Fermions, the answer to life, the universe, and everything. Who recognizes this quote? So what? I don't know that one, but the Hitchhiker's Guide to... that is the same? I am demonstrating what I wanted to show you because this is a very famous book here in the US. But we don't know this book in Holland. So the joke of this headline was completely missed by the Dutch press. They saw this headline in the international news and they came with their own they follow-ups. So what did they write? You don't know. There's really nobody who can read Dutch? No. Okay, so you cannot check, but the translation goes as follows. The nothing particle can cause revolution. Yeah? Or this one. This is actually from RTL. This is a sort of the Fox News, national big news. And it translates as important, but not sexy. A particle discovered. And I know here in the US you have this X rating for explicit language. This is kind of an inverse X rating. It warns people, and mostly teenagers, careful, this item does not contain explicit language. And in fact, I think it's even worse if you think about it, that what it does do is it actually warns people, be careful, this article contains science. I think that's exactly what it does. And that's what actually makes me a suspect in Holland. Okay, but let me very quickly flash this one. A non-existing particle discovered. Not entirely accurate. Or an elementary particle discovered in Delft. And this elementary is also not entirely correct. So I think I need to clear up a little bit this confusion. But, it made us some kind of celebrities in Holland. But all based on this misunderstanding of the Hitchhiker's Guide to the Galaxy. Okay, what is this confusion? Well, the confusion is a little bit in basically when we hear about particles, they all come from accelerators and from the cosmos and so on. So we always think about particles in terms of elementary particles. So I've given a little scheme of the universe and all the particles in the universe with a dividing line somewhere here. And if you go to the left, you find the nice dictionary of elementary particles, like the electron, the neutrino, and if you put them together, they can form a proton and a neutron, and so on. The Higgs particle is also on this side. So many of the particles from the news, the Higgs and also the neutrino, remember, they went faster than the speed of light until the cable was fixed. But all these particles are the subatomic elementary particles, and they're also called fundamental particles. Now on the right side, we have the atoms, the molecules, and all the composite or collective pieces of matter. They are built out of atoms, which are built out of electrons and protons and neutrons, etc. So here we have the composite or collective particles. But I would also claim that also these particles are fundamental. We exist out of these particles, and I don't know. That's a point of view, but I would call that still fundamental. They're equal in their fundamentalness, I would say. Now and this is actually also a dividing line. The cosmic particle, or the texts that are focused on the Majorana from the cosmos, they look for a particle in this zone, whereas we are working in this zone of composite materials. Now, composite or collective phenomena should not be viewed as something weak, that if you can break it. The principle is you can. They are not elementary, so you can break it. But if you do it right, these composite molecules or materials, or even the phenomena that result from it, can be extremely strong. This is a picture that illustrates it. Another picture is this train. And from a running train, it is very difficult to derail one of the wagons. It's actually the connection between all the wagons that makes an individual wagon very, very strong. And this is kind of the picture that we have about phenomena like superconductivity, where all the electrons are condensed in the same piece of state, a collective behavior, which makes it very robust and very strong. And superconductivity is extremely strong. It's a phenomena that is so amazingly accurately quantized that it's beyond imagination. And the picture that we have is a little bit like the train, where it's becoming very stable, because they're all connected. You cannot push out one of the wagons. And this is also the approach that we follow to make these Majorana particles. We actually make a one-dimensional train, not out of these wagons, but out of electrons. And the picture that I have is the following. So we start off with electrons, and my orange balls are electrons. And we put them in a row, and we leave one seat open on the left. There's a hole, an empty seat on the left. And if we can ask all these electrons, well, could you all move over one seat? And that frees the seat on the right. It's actually very powerful what I've just done, because you just ask the collective row of electrons to move, and the empty seat jumps over from here to here. And this could be a long distance. There's actually no restriction to this distance. This empty seat can jump over in very little time to the other end, very far away. So I can do this quick, and you ask the people. The electrons learn fast, so they go back and forth, and the open seat jumps back and forth very quickly. Well, so fast that, in fact, if you treat it quantum mechanically, the right drawing is something like this. But they're no longer jumping back and forth, but the seat on the left is always half empty and half occupied. Same is true for the seat on the right. But these two seats now are in a superposition, and I will say a few words about superposition. These seats are in a superposition of being occupied and empty. And this is the quantumness that now comes in, that We no longer have things that go back and forth even very quickly, but at the same time, it's occupied and empty. This half occupation brings me back to my glasses. So it's like the half-filled glass, or half-empty glass. I'm an optimist. Which, if we put them together, what we can construct out of it is one full glass, one empty glass. Now let me rearrange these glasses a little bit to make an equation. So now we have two glasses on half glasses on the left, which makes up for the superposition. So these two half-filled glasses in quantum language make up for the superposition of being filled simultaneously with being empty. You can do the math and you see it actually, there's the same amount of liquid on each side. And this is the quantum superposition that we're using. And those Majorana Fermions, still in picture format, one pair actually encodes for 0, the empty glass, or 1, fermion. If I divide the thing by 2, it actually says, it's what actually many people say, that a Majorana Fermion, a Majorana is half a fermion. So if I take just one of them, I should multiply this by 1/2, so the Majorana is half a fermion. But this picture that a Majorana is a superposition of being filled and empty at the same time, that is the correct picture. In picture form, and if you write it out, then the Majorana is the superposition with a factor of 1/2 of 1 electron and 1 hole. That's the thing. So it's two particles at the same time. That makes it a Majorana. Now, to ensure that this factor 1/2 is exact, because it wouldn't work with 3/4 and 1/4, it has to be 1/2 exactly. That is ensured by connecting our piece of material to a superconductor. So this superconductor ensures that you have this factor 1/2 in front. And that makes this end particle here and this end particle there fulfill the definition of Majorana. Now this picture of our, let's say, effort is actually a translation of 2 theoretical papers that came out only 2 years ago, 2.5 years ago. And one paper was by Roman Luchin, who was actually here at Station Q, Kei Sao, and Sankar Desarma. And I'm actually not sure if these people are in the audience. Sankar, are you? Okay, very good. So these people are actually here in the audience, and they laid out a recipe of what experimentalists like me exactly had to do in order, to construct these Majorana fermions. And that's the picture format and the equations you can find in the first paper, as well as in a very similar paper by Yuval Orek, Gil Raphael, and Felix van Oppen. So we followed these theoretical proposals. So what did we do precisely? We need this wire, we need to fill it with electrons, and we need to connect it to a superconductor. So let's do that. So the wires is actually our expertise. If there's anything that I can do well, then I can play with these wires. And we make these wires in collaboration with a former student who's now in Eindhoven. This is made by some MOCVD, some growth mechanism, which grows these wires out of a little catalytic particle, which actually always stays on top. And it has a nano-size diameter and a length which can be in the microns. Actually, it can actually be hundreds of microns. And this is very narrow, right? This is 1,000 times thinner than a hair that we can barely see with our eyes. So we take these wires and we make a chip out of it. So what you see on this chip is, first of all, blue. And blue is the surface of the chip. And below the surface, we've actually already prefabricated a whole set of gate electrodes, so metal stripes, which we can use to apply electrostatic potentials to change the properties in our system. Then we have in green the nanowire, the semiconducting nanowire, which connects to a piece of gold, which is a metal, on the one end, and a piece of superconductor on the other hand, in red. So this is our system. This combination of materials with metal. It's actually a beautiful combination because the substrate, the blue part, is insulating. It's a dielectric. Then we have a metal. Then we have a semiconductor, and then we have a superconductor. So what else? It's pretty much everything we have in terms of materials. Now in this scheme, and I said that the Majoranas sit where the superconductor touches the wire, and the Majoranas have to sit at the end, at the half-open spaces, so at this point and at this point. These are the two locations of the Majoranas. Now we know that the metal has electrons in it, and these electrons are just individual electrons that can move around in a metal that give you electricity. And we know that the superconductor has paired electrons. So the basic particle in a superconductor is a Cooper pair, which means that all the electrons are paired in pairs of 2. So that gives us a problem, right? So if we send electrical current from here and out there, these electrons, via this piece of semiconductor, somehow have to pair up. They can only cross the superconductor if they find a partner. So each electron has to find a partner, and then they can maybe toast or something. And I promise you that we can explain our experiment in terms of the half-filled, half-empty glass. So the electrons are the filled glass. The Majorana is here depicted as the half-filled, half-empty, whereas the Cooper pair are, you can toast, you go out as a pair. Yeah? In Holland, I usually tell the story of a singles, an evening, a party with singles. But at the end of the evening, they have to leave as a pair and they can toast. But at the door, they have to find a partner. And in this case, you could never find the right partner to hook up, with 2 full glasses. But fortunately, this glass is not just half full, half empty. It's actually a superposition of being completely full and completely empty. So if this electron finds the full part of the Majorana, then it can pair up in a Cooper pair and continue into the superconductor. This is actually exactly what's happening. The electrons, when we send them in, and the electron actually combines with the full part of the Majorana and then continues as a Cooper pair out of the system. So let's look at the experiment. We do an electrical measurement, so we measure currents and voltages, and then we measure basically the conductance for different values of the magnetic field. At the lowest curve that you see here, actually where there's a little peak here, comes down, a little peak here. Now the peak on the right and the peak on the left, that tells us about superconductivity. These 2 peaks, we know them as the signatures. We have a superconductor in our system. Fine, that's good. But then actually, nothing eventful is happening. It's just a smooth curve that connects these 2 peaks. But if we turn on the magnetic field, and these adjacent traces, actually they are taken at successively higher magnetic fields up to half a Tesla. If you zoom in on the section in the middle, then that section is actually zooming in on the 0 voltage axis. And 0 voltage actually defines 0 energy in our system. And the peak that arises after applying some magnetic field here, that stays on at 0 voltage all the way up to this field of, about a few tenths of a Tesla. And this is the first signature that we were looking for. It's a peak at 0 energy. So this peak corresponds to an underlying state, or loosely speaking, a particle that lives at 0 energy. Now, actually more important than just seeing something at 0 energy is the observation that it stays at 0 energy while varying the magnetic field. If this particle would have a magnetic moment, a spin or something like that, it would move away from 0 with a Zeeman energy. Everything that has a magnetic moment, you put 2 magnets and there's a force and it introduces energy. So the fact that this does not move away from 0 energy means automatically that this particle is not magnetic. Okay. It's not magnetic. So next is, let's take one of these curves and now apply an electric field. We have all these gates underneath, so now, let's apply voltages, create electric fields. Again, you see a peak at 0 voltage, and also in this case, it does not move away from 0. We apply electric fields over quite some range, but it stays put at 0 voltage. So also in this case, what it means is, it's not electrically charged. If you apply an electric field and the state would be charged, it would move, get energy. So these are two of the checks. Now let me show you a little bit the size of our peak, because let me see if this works. Now this is actually a three-dimensional representation of the data, and these big things, red things, are the shoulders coming from the superconductivity, and the little peak in the middle, that's our sweet little peak. That's our signature. The Higgs particle also, had a little peak and was sufficient to identify it as a particle. And this is our sweet little peak. At 0, always at 0. Then the question arises, can you also make it go away? If it's always there, okay, but can you make it go away? And to do that, what we've done, actually, it's a very detailed measurement, but we like it actually very much, is that we need a magnetic field to introduce this state, or this particle. But what we've done in this measurement is, if the wire is directed along this axis, we've changed the direction of the magnetic field over a sphere. And actually, the particle should only be there under certain directions. So if you take it from the theory papers, it should not always exist, but only under certain directions of the magnetic field. And this set of measurements, actually a lot of measurements in this color scale plot, I can lift out some curves, for instance the green one, which there's no peak at 0, whereas if I change the angle, there is a peak right there at 0. It was a very important measurement to identify the underlying particles. This data was published in the paper in April. But I also brought some new data that I will present. We have a conference this week on Majorana Fermions, and I brought some new data that is brand new and it's unpublished, and actually I've not shown it before. But I thought it would be nice to also give you, sort of a peek preview on something new. So it's, you need a loving eye. This is data that just comes straight out of the lab. It's unpublished, but this is the data, and actually we like it very much because we are actually trained by now to look at these plots and see beautiful features in here. You probably see a blur, but I see some very profound action here. So here's the 0 voltage axis. There's the bias voltage, positive and negative. Here's 0 voltage as a function of magnetic field. And indeed, if I follow this axis, and there's nothing, actually there's no peak at all, but here the peak starts. The field of about 0.6 Tesla or so. And the peak stays there, but here the peak actually starts to split. There's actually a split peak. But then it merges back to a single peak. Here you see it, you can clearly see it, a big peak over here. And then it actually starts splitting right over there. So our peak is not always at 0. It's actually, it's at 0, then it sort of splits. And I can show you that my trained eye is actually really telling you the right thing. But if I show you some cuts through here, then along this line, we have the cut with two, there's a little one on the left, but there's a visible one on the right, the split peak. This cut is the single peak right here, very visible, at 0 voltage. And then along the blue line on the right, we clearly see a split peak. So the peak can split. And we are excited about this, and we're very excited about that we present this data this week at the conference, because a month ago, this paper came out from, again, Sanko de Sarma, Jay Sao, and Tudor Stanescu, just a month ago, they said there's a Majorana smoking gun for this system. And the smoking gun is at the peak has a splitting that has an oscillatory dependence on the Zeeman field. This is, actually what we measure. That is another smoking gun that would identify the Majorana fermion. It's unclear how many smoking guns you actually need before you can sort of, make a verdict, but this is not a smoking gun. And actually today, so it's very exciting times, because today such a splitting was also reported by the Marcus group, together with his former student, Hugh Churchill. And so things are, collecting and building up. All right, so let me evaluate this. And so we actually evaluated ourselves. And actually at the day when the paper was published, we actually went to a bar, the Odeon, Café de Odeon, to celebrate it. And before saying this, let me first mention that I was saying already that these experiments are done by several groups, particularly on nanowires, semiconductor nanowires. I've listed 3 of them from Lund, Weizmann, and the Harvard-Copenhagen combination, where similar results are coming out. So the evidence is building up and things are reproduced. But we were celebrating that day the outcome of the paper together with the authors of the paper. So this was my student Koen Joao, my student Vincent Maurik, my postdoc Sergei Frolov, and the 2 people who made the material, the growers, Sebastian Plizar and Erik Bakkers. And you see, we're looking pretty happy here. And it's not only because we were already spending a couple of hours at this Café de Odeon, but it was also because we saw actually the journal Science itself and the cover that the journal chose for the publication. And that journal was actually giving us a signature of the man, Ettore Majorana. Not only did the paper report on the measurements of the particle, but also the man was visible there. Now what we saw when we found the published paper, the hard copy paper, was that the editor had actually chosen this as a cover. Of course, we had a suspicion because we actually submitted those covers ourselves. But first of all, we had submitted the one on the right, which is actually a photo of the actual device, colorized in some Photoshop program, but it clearly shows the metal, the wire, and the semiconductor. And there was another student who was actually very good in Photoshop, who made an artist impression of the device, and including some little pieces here, squares, and what have you. Nobody knows what it is. But the art director of Science magazine liked it, obviously, and picked this version for the cover. What the art director did not see was a little thing that was sort of hidden in the picture. And I said it was, a signature of the man. And where can you find the man? The man must also, sit at the end of the wire. So if we zoom in, maybe you can already see a little bit. We can actually zoom in on this piece of wire. There's actually a picture, and we thought, who is this man? And then we found on the internet a picture of Ettore Majorana, and it was actually the same guy. So let me stop here with this tribute to Ettore Majorana, and thank you for your attention. Thank you very much.
As you know, it's our tradition to take questions. I also just want to highlight, to me, the joy in seeing such strong interplay between theory and experiment. Mm-hmm. As a theorist, it's great to see when that happens. So, first question. I wait for the mic.
That was wonderful talk. So I have kind of a rude question. Do these composite particles really count? I mean, is this
count as?
I mean, is this really a Majorana particle, or? Are people still gonna want to find the elementary particle?
Absolutely. No, absolutely. And they should. And it would be, if people in the particle physics can also identify and detect let's say the cosmic Majorana fermion, it would be a great discovery. Also, what I mentioned in the context of dark matter, it could, maybe it's the candidate that explains dark matter. It would be a huge discovery. Our, let's say, Majorana, I think, formally should be described as a quantum state, and that quantum eigenstate of the system obeys exactly those definitions of the Majorana symmetry relation. So in that sense, it's completely the same. Well, this chair is for real. It's a composite material. Many of these collective things are really for real. I think you and I are,
So early in the talk, you talked about particles and antiparticles having negative energy of each other. So I wanted to ask, what does that mean in context to have negative energy? And then when you start talking about these Majorana particles having zero energy but a non-zero mass, how do you correlate that with the relativistic energy of E equals mc squared?
Well, the reason I was saying is that maybe you are familiar with this picture from Dirac where there's this cone of all the possible states that he could define. And he defined the positive side as the particle side. And below it was the sea of filled, the infinite sea of filled states. And if you take a particle out from there, then you create a hole, the antiparticle. Right? So a positron out of electron. So that there's this symmetry, and the Majorana fermion lives exactly at the crossing point. It's at that point where you have this symmetry of particle being equal to its antiparticle. Now, the thing about the mass is actually, I actually don't think it's completely resolved. So in our case, we speak about mass as an effective mass in condensed matter physics. And in fact, in I think all cases, I'm not sure in all cases, but in most cases, the mass is zero in our case. In the context of neutrinos, the story is also a bit complicated because there the mass of the neutrinos actually oscillates between the various neutrino states. And we know these neutrino particles actually oscillate between different states, so they can actually get mass, no mass, or it's a confusing story. But that should be connected to the mass of the Majorana. And there's a particular particle physics scheme where you can pinpoint whether neutrinos are Majoranas or not. Please. Yeah.
What is a superconductor and what temperature do you operate at?
Very good question. So we operate at the lowest temperatures in our dilution refrigerators, which is very close to the absolute zero. So it's just it's actually less. It's 1/10 of a degree above the absolute 0 point, so 0.1 Kelvin. But this is a machine that we have, and we push the on button, and it goes to that temperature. And a superconductor is actually what the word says. It conducts electricity without dissipation. So it has no resistance, and that's why we call it.
Which material?
The material that we use is an alloy of niobium titanium nitride. And we find that this alloy is actually, because usually superconductors die if you put it in a magnetic field, except if you make certain alloys, and this is one of these alloys. It's actually a very important experimental part of the work to get the right superconductor. There's Lars, there's...
You were saying that the particle itself wasn't magnetic or it wasn't electronic or electrical, but you showed that there was different behavior as you moved through different magnetic and different voltages. Why would that be?
I can... let me go. Is this the right graph? Or, yeah. So I think if I put these words in a bit more official language, the particle is not magnetic. What it means is that there are no internal degrees of freedom of that particle that has a magnetic moment, a magnetic state. So there's nothing inside the particle that could still react on a magnetic field. And so that's not there. So in that sense, it's not magnetic. Now, the background of these pictures has a lot of ununderstood stuff in it. And so in fact, for the ideal case, this conductance should drop right here completely to zero, stay zero, and then climb up again. So there's this background conductance that flows inside the superconducting gap, and it's only on top of this background conductance that we find this peak that is insensitive to magnetic fields and electric fields. So in that sense, there's still some cleaning up to do to really make it the ideal Majorana fermion. This all has to be, we have to get it under control.
So in the diagram you showed with all the electrons lined up, and at first you showed one missing and one full, but in fact they're superimposed. Is it correct that they are not a pair so that they both join up with another electron, or does only one of them join up, and then what happens to the other one?
If we shoot in electrons?
No, I'm looking
at the bit. Okay, so let me first maybe point out that they always come in pairs. They can only exist in pairs. You cannot have
in the wire.
Yeah, well, actually, always. So also here, maybe it's go to this one.
Right. The image with the superconductor that had the two little star signs showing where the superpositioned.
Yeah. Yeah, it's. Let me find this slide.
Go ahead, about 5 slides.
Yeah. I have this convenient trick on the computer which I cannot find. So now I go to the knob.
Right.
Here.
So if the higher one acts as if it's full and pairs up, does the other one do the same thing, or is it not able to do that?
It's actually the combined state. It's so what the simplification here is that the combined state actually defines this having 0 or 1 fermion in the system, and in this combined state you can either add one or you cannot add one, and this is actually giving you this pairing. So you cannot say that here is one. Let's say full glass. It's actually spread out over the system. It's a collective state.
Hi, I'm a little confused about the Zeeman splitting. So if you were able to split it a la Zeeman style, it implies an internal magnetic moment.
Mm-hmm.
And when you do split it, then it's not zero energy anymore.
Right.
So it's not a Majorana particle.
Exactly.
Anymore. So what do you? I don't understand why that was good.
No, so we did. I've only showing you. Where is my? Here it is. Showing you sort of a subset of all the experiments.
Is there a predicted Stark splitting too? Not yet.
No, I don't think so.
It was actually after that.
So if we do the same experiment with an electron,
yeah,
and apply a magnetic field, then the electron has a spin up and a spin down. Then in the presence of a magnetic field, one goes up in energy and the other one goes down. And we've done it many times. Many people have done it many times. And what you see is sort of two states that then go out. And that tells you there's an internal degree of freedom which has a magnetic moment, and you can lift the degeneracy at zero magnetic field by applying a magnetic field that brings the two states apart. And here the curious thing is that whatever we do, it just, it stays at zero.
He was asking about the most recent data you showed.
Yeah, it was way after that. Way after that.
This, The splitting is really, new and fresh, and I cannot claim to understand all the details.
Keep going. More. It's real clear later.
Well, this is one of those shows of splitting.
To you, but not to me. So. There we go.
Yeah.
Bottom left.
Yeah.
So those
Yeah.
states are not at zero energy anymore.
Right. And this state is Majorana-ish. But not, it's not the Majorana that we're seeking. So the story is as follows: that there's a zero peak at zero energy when the two Majoranas are actually far away from each other. If they are too close together, they can still interact. Their quantum mechanical wave functions, or their reach, can actually start feeling each other, and this interaction will then cause a splitting. So as long as they don't feel each other, they're far away from each other, then there's a single peak. But if they are not so far away each other and they can interact, the peak splits. So it's actually a signature of the interaction between two Majoranas.
Yeah, maybe I should quickly comment on this question. This splitting is not Zeeman splitting.
It's not Zeeman splitting.
So your question was that these are pseudo Majorana, they're split, but then they come back together again. So this is not like splitting that would happen to electron if you apply a magnetic field. It is splitting, but it's very different kind of splitting. So it's not Zeeman.
And this answer was given to you by the first author of this paper.
I'm curious whether making a discovery like this, how many physicists that are working on other things have had all of their past research pretty much topped by this, and what do they do for a living now?
Sorry, pretty much. Sorry, I
want you to repeat the question.
I missed the clue. I'm Dutch.
I said,
famous for missing the clue.
I'm curious whether this discovery, how many physicists around the world have been working on other research that because of your discovery now, their research all of a sudden has been proven to have a severe thunderstorm over it, or it's just, it's no longer valid. And what do they do from now on out?
No. I don't think that is the case here. Actually, the recipe that was given by those theoretical papers is actually quite specific. You really need to do something, very specific, like a particular semiconductor, not all semiconductors. It's actually only this indium and timonite with a strong spin-orbit interaction and a huge G factor that has to connect to a superconductor, not every superconductor, but the one that actually stays alive in a magnetic field. And you have to go to a regime where the number of electrons in the wire is actually very low density. So there are a bunch of requirements that I don't think anybody has ever, by luck, combined in one single experiment. This was not a lucky, serendipitous discovery. It was, straight engineering to the answer.
I have a question. I'm one of the people that has roughly no idea what you've talked about. But if you would go back one slide to the Twin Peaks again. If the particle has no charge and no spin, how does bringing them closer together when all they have is undefined mass cause them to affect each other?
You didn't understand it? No,
I warned him the questions would be really good. So.
Let me use this picture, or let me maybe even use this picture. The way we move over the empty seat is by let me just put it in first in terms of seats and balls and so on. We just move this one over and then move this one over and move this one over. So this empty thing that maybe has no charge or no nothing is moved over by the movement of the others. And so we can move the Majorana by moving the other pieces. And in our experiment, what we actually have not done yet, but we plan to do that in a controlled way, is to this region of where we have this superconductivity induced into the semiconductor. We make that region smaller and smaller, and then the end point will actually move in, and the end point will drag the Majorana along. So we're not directly coupling into the Majorana with the electric and magnetic fields, but we're moving the end points. It is a superconducting proximity effect.
You end up eliminating that when you effectively only have a electron that is in a sense not having either proximity or I call it electron friction that's sort of causing this attraction.
I'm not sure if I can connect to the friction.
Well, I'm trying to describe it in layman's language.
Yeah. Well, you know, I'm sorry. Yeah.
In and of itself creates an effect.
Well, you know, just think of cutting, you know, pieces from the wire. I make the wire shorter. I cut it. Then the end point will actually move. And the Majorana will always sit at the end point. So if I cut the wire to shorter and shorter length scales, then the Majorana will actually move along with the end point. Then the Majorana splits and it becomes Majorana-ish before it completely becomes a normal electron. Yes, there's a transition region where it loses its Majorana properties. Yeah.
Next to last question.
What is the connection, the potential connection with dark matter?
I should actually ask the chairman, but no. Okay, so actually there's a very nice, I think, story to it. Is that we know of dark matter because we see in the cosmos gravitational forces, but we have no clue what actually causes it because there's no mass that we can actually detect. It's not visible. We have no detector that actually can measure the thing that causes the gravitational forces. So that's why it's called dark matter. Now the Majorana is also very dark because it's very difficult to detect. It has no properties, or all the properties are equal to 0 except for the mass. And there's actually a theoretical idea, I guess. It's called supersymmetry, that says that all the particles have supersymmetric partners. So not only particle-antiparticle, but also all the bosons that we have, like light particles, the photons, have a supersymmetric partner which still obeys this symmetry relation of particle being equal to antiparticle. And that, in the case of Majoranas, could be a candidate, is one of the candidates for the dark matter. So it's a very interesting story, actually, but a little bit outside the scope of my work. A little bit far away from but very interesting.
I was curious, is this only for 1D, or could you scale it to 3D? And I guess the second question is also just what are the future applications for this?
Yeah, so in 1D, in 1D we have two well-defined endpoints where the Majoranas are confined and localized. If it becomes 2D, like the table here, then the Majorana can flow around the table. So it becomes actually more one-dimensional. Instead of having a small confined region, it becomes an extended one-dimensional region. And if it's a three-dimensional system, it can actually live everywhere on the surface. So it becomes completely delocalized, and you can find it somewhere on the surface. But only in 1D they become localized.
Great. Well, let's thank Leo again.
Thank you for your attention.
So just to remind everybody, we have reception out in the courtyard area. Also, Derek, can you stand up and wave? So Derek's the chair of the Friends. For those of you who want to understand what the Friends are, you can find Derek at the reception. And there's folders over here. So everyone, if you have more questions, of course, Leo will stay here till you're done with them. So thank you for coming.